This is the first video that I'm going to be recording for Chapter 4 of Pre-Calculus 11. So Chapter 4 is all about quadratic equations, and it comes after Chapter 3, which is all about quadratic functions. So if you haven't gone through Chapter 3 already, make sure you start there, because otherwise this chapter is not going to make any sense to you. So Chapter 4, all about solving different kinds of quadratic equations, and it's going to go through some different methods. Section 4.1, which is what this video is specifically about solving by graphing, which is what the title is. But before we get to that, let's talk quadratic equations. What are they? So a quadratic equation is pretty similar to a quadratic function, which is what you would have covered in Chapter 3, with one key difference. So a quadratic equation is basically just a quadratic function, but it's a quadratic function that's not going to be equal to y or to f of x or anything like that. Instead, it's a quadratic function that has a definite value, so it's going to be equal to a number, usually 0, but not always. So, for example, that might look something like, if we want to get general, ax squared plus bx plus c equals 0. Or if you want something specific with some numbers, 3x squared plus 7x minus 2 equals 0, for example, would be a pretty typical looking quadratic equation. And like I said, we can solve these things by graphing. We're actually going to see 4 different methods, but this is the first because you already have pretty much all of the skills you need. You'll find the solving part is actually pretty easy. But you can't graph an equation that's equal to 0, so we're actually going to go back to those quadratic functions from Chapter 3 and graph the corresponding quadratic function. So that basically just means you're going to swap out the 0 for a y. So, for example, if I wanted to solve the equation x squared minus 2x minus 3 equals 0. So remember, when you're solving, you want to figure out the values for your variable, which in this case x, that are going to make your equation true. So what number, if I put it into here, would actually give me 0 as its overall value? When you were solving linear equations in the past, that was pretty easy because you could just isolate the variable. You get x by its own, you do opposite operations and all that. The problem here is there's 2 x's, and we can't combine them or anything like that because one of them's a square and one of them's just an x. So we can't isolate here, at least not with where we're at right now, which is why we need to go a different route. So to solve, we're going to graph that corresponding equation like I talked about. Y equals x squared minus 2x minus 3. So again, same overall thing, just we've swapped the y out in for 0. All right, so if you haven't already learned how to graph quadratic functions, you should probably go back and look at that because this is going to be pretty much impossible for you. So step 1, we want to graph this. Looking at it right now, it's not in vertex form, so graphing it where we are right now is going to be kind of annoying. So the first thing we should probably do is complete the square if we have to. If it's already in vertex form, great, but if it's not, like this one here, we're going to start by completing the square. All right, so we've got y equals x squared minus 2x minus 3. I'm going to move through this pretty quickly, so if you don't remember how to complete the square, pop back to section 3.3 and look at the videos for that. So we throw some brackets around our first 2 terms. We're going to take that negative 2, we're going to divide it by 2 to get 1, and then we're going to square that to also get 1. So that's y equals x squared minus 2x plus 1, and then minus 1, because we're going to add and subtract that number we got, minus 3. We're going to move that negative 1 out of the brackets, so we're going to get y equals x squared minus 2x plus 1 minus 3 minus 1. And then lastly, we're going to simplify the stuff on the outside, and we're going to factor that set of brackets, which is going to get us x minus 1 squared minus 4. So there we go. It's in vertex form. It's great. So that was step 1. Step 2, which is where most of the work for this process is going to be, is just graph. So you should already know how to complete the square. You should already know how to graph. So most of this process should all be stuff that's familiar for you. So we're going to get ourselves a 5x5 grid here. And we're just going to get ourselves a graph. All right, so quick refresher on graphing. This is in vertex form. We get our vertex from P and Q. So vertex is right there. And then from there, we've got 2 options for how to graph. We can make a table of values with the vertex in the middle. So if that's 1, then we're going to get points at 2 and 3 and 0 and -1. Or you can use the pattern. I'll use the pattern for a future example, but just to refresh people on sort of the more basic way of doing things, we're just going to plug some numbers into our equation here. So we've got y equals, and let's start with 3. So we're going to do 3 minus 1 squared minus 4. And then we just follow BEDMAS. So 3 minus 1 is 2. 2 squared is 4. And 4 minus 4 gets us 0. So when x is 3, y is 0. We already know from the vertex that when x is 1, y is -4. And then symmetry, remember, if y is 0 when x is 3, that also means y will be 0 when x is -1. So we do that again with another point. We'll put 2 in there. 2 minus 1 squared is 1 squared. 1 squared is 1. And 1 minus 4 is -3. So there we go. We got some points. So we're going to go ahead and plot those on our graph. And I actually am going to want one more set of points here for reasons that will be explained later. So let's go ahead and plug 4 into here as well. And so 4 minus 1 is 3. 3 squared is 9. And then 9 minus 4 is 5. So we're also going to get points a little bit further at 5. So that's these 2 points right here. Okay, so we've got enough points. Let's make ourselves a parabola. We want to be as accurate as possible here. It won't matter a ton on this one, because on this one the solving is going to be pretty easy. But you will see there will be some later where it's going to be incredibly important to have as good of a graph as you can. Okay, so we have completed the square. We've got a graph. So step 3, on to the actual solving part of this. Right, everything up to now has just been chapter 3 stuff. Now we're stepping into chapter 4, solving our equation. And you're going to find it's pretty easy. So to solve the equation, we're going to find the points that make the equation true. But thankfully, that's really easy to do. So if you compare our equation with our function, remember we had y equals x squared minus 2x minus 3, or we had x squared minus 2x minus 3 equals 0. So the middle parts of both of those are the same. The only difference is that one of them is equal to y, and one of them is equal to 0. So if we want these two things to match, what we're really saying is that we want to find the places where y equals 0. Right? That will make the equation and the function a match. So if you stop and think for a second, if we look at our graph, y being 0, well, that's this line here. That's our y-axis, or sorry, our x-axis. And so if we want to find the points where the graph matches there, we're really trying to just find the intercepts, specifically the x-intercepts. So we want this and this. Those are our 2 points. So to solve, find the x-intercepts. That's really it. That's the only thing in Chapter 4 that's different from graphing in Chapter 3. You draw the graph, you find your intercepts. So in this case, our solution is x equals 3 or x equals -1. Those are the 2 points that make this equation true. And those two numbers just came from these two intercepts, +3, -1. All right, so let's try it with another one. So we're going to solve 3x squared minus 12x plus 12 equals 0. One more quick refresher on completing the square. So remember, when there's an a value out front, like there is here, we're going to have to take out that a value. Right? So a in our vertex form is on the outside of the brackets, so we need to do that. But when you take it out, you got to remember to take it out from both of these terms, or else you're going to run into some problems. Oops. I've also made a small mistake here. You notice how I have equals 0 on the end of both of these? That shouldn't be there because we've taken the 0 and we've swapped it out for the y. So get rid of those zeros. All right. Going through the rest of the process, we divide by 2, we square, we add and subtract. Then remember, when we move that -4 out of our brackets, we're going to have to remember to multiply it by this a value. So those two things are going to get multiplied together. And then we factor and we simplify. And what we end up with is y equals 3, and then just x plus 2 squared. So same deal. We're going to graph this carefully. A 5 by 5 will do. So go ahead and get yourself a graph. And let's see what we come up with. All right, so looking at this, our vertex, our p-value is 2. There is no q, right? The 12 is canceled out, so q is just 0. So our vertex then is going to be at 2, 0. Oh, I actually made another mistake. So if you look at my completed the square version, I swapped from a -4 to a +4 for some reason. It's a really common mistake to make, but it's not a great one to make. So let's go back and change all those to minuses instead of pluses in our brackets. So it should be x minus 2, not x plus 2. All right, so that means our vertex is at +2 and 0, right there. If I want to graph this without having to make a big table of values, remember we have a shortcut that we can use. So we're going to make a pattern. So the basic pattern, if you remember hopefully, is over 1, up 1, over 2, up 4, and over 3, up 9. So remember, we're just squaring the horizontal distances to get the vertical. 1 squared is 1, 2 squared is 4, 3 squared is 9. But we have an a value here, so all of these vertical distances, 1, 4, and 9, all get multiplied by 3. Now what that means is most of these points aren't going to fit on our graph, but it's actually not going to really matter much here. Typically, I'm not going to let you get away with a graph with only 3 points, but you'll see why it doesn't matter. So from our vertex, we're going to go over 1, up 1 on both sides. And that's all that's really going to fit, because I don't really feel like going up 12, which is what we would have to have done, right? Over 1 up 3, over 2 up 12, and over 3 up 27. But keeping in mind, our main goal here was to figure out our solutions, and our solutions are always located at our x-intercepts. And we actually already knew where the x-intercept was before we even started graphing because, well, our vertex was on our x-intercept. So our solution to this equation is just x equals 2. We've only got the one x-intercept. So anytime your vertex is on your x-axis, that actually just gives you your solution straight up. All right, so let's try another one. I'm going to challenge you to do this one for yourselves. So you're going to solve -2 times x plus 1 squared minus 1 equals 0. So I've given it to you in vertex form. You don't have to worry about that. I will warn you, you're going to have a graph that's probably going down pretty far. I would say maybe go down to -10, go up to probably about 2, and then go left and right to just -5 and +5. So go ahead, get yourself a set of axes set up, get your graph up there, and see if you can figure out what your solutions are. Okay, so I've got my axes all ready to go. Our vertex, just comes from our vertex form, is at -1, -1. So that's going to be right here. Let's zoom in a bit on that. And then our pattern, since A is -2, instead of 1 and 1, 2 and 4, if we multiply those vertical distances by -2, we're going to be going over 1 and down 2, and then over 2 and down 8. So over 1, down 2, and over 2, down 8. And so some of you probably pretty quickly noticed that something was going to be a little wrong with this one. Our parabola is going to look lovely, but in terms of what we were hoping to accomplish with this question, we run into a bit of an issue here. So remember, our goal is to solve our equation. And to solve our equation, we wanted to find x-intercepts, but this particular graph doesn't have any. So if you stop and think about that for a second, well, what does it mean if we've got no intercepts? That means our solution, or rather our equation, doesn't actually have any solutions, which can happen. So that's probably a new thing for you. So when you're dealing with linear equations back in grade 7, grade 8, grade 9, those always had a solution. There was always an x value that made them work. But quadratic equations, it's not always going to be the case. There isn't always going to be a number that will make things work out. Right? For a really obvious example of that, if you think of the equation x squared equals -1. So what number squared would give you a negative? Well, there's not really anything, right? If you square a positive, you get a positive. If you square a negative, you get a positive. And so there's no number that's ever going to make this equation true. We'll deal with ones that look like that a lot more maybe in section 4.3, 4.4. So in the grand scheme of this, the way this works is we can have 0, 1, or 2 solutions. So just a quick sketch of what those 3 situations look like. 0 solutions is exactly what we just described. So that's a graph that has no x-intercepts. 1 solution, we also saw earlier, is where your vertex is an x-intercept. Doesn't matter whether it's pointing up or down, whether it's on the left or the right. All that matters is your vertex is on the axis. And then 2 is basically the opposite of 0. So it would look something like this, or like this. And so to think about this, think about, once you've got it in vertex form, which direction your parabola is facing and where the vertex is. So if it starts above the x-axis, so your vertex is above the x-axis, and it keeps going up, like, say, this one in the top left here, that's never going to have any solutions. But if it starts above the axis and then it goes down, like this one down here, that will. So you got to consider that. You can save yourself some work. So if you looked at this question and you thought to yourself ahead of time, oh, hey, I know where the vertex is and I know it's going in the wrong direction to do anything productive, you wouldn't have actually had to have graphed this. You could have just said, no solutions. Okay, let's give you another one of these to practice. This one will have solutions, I promise. So you're going to solve negative x plus 3 squared plus 5. A 5 by 5 by 5 by 5 grid will do great on this one. So go ahead, get that all set up, get yourself a graph, and then come back and see how you did. You're going to notice something a little bit weird about the solutions on this one. So we're going to talk about that once you've got it graphed. All right, so your vertex should be at 3, 5. The graph is going down, not up, but it's not stretched in any way because the a value is 1. So our pattern is the same, just pointing in the other direction. And so you'll notice after getting 5 points, you don't have enough. You haven't crossed the axis yet, so you don't actually know where your solutions are. And we might actually need to extend our axis a little bit further out here, so maybe let's put that to 6 instead of to 5. All right, so over 1, over 2, and then now over 3 and down 9 gets me a point here and a point there. Great. So I'm going to draw myself a parabola, and then we're going to see that this one's a little different than the ones that we've done. The parabola itself looks fine. But remember, once again, our goal is to find intercepts. But if you look at this graph a little more closely, you'll see that those intercepts aren't clean. They're not exact points. That's fine. So what you do in cases like this is you're just going to have to estimate. So you can't say 5 and 1. That's a pretty common mistake people make. This intercept's not at 5. You know it's not at 5, especially because we already have a point at 5. And you can't have 2 points that are like above and below each other. These things are constantly going outwards. So don't ever make the mistake of using or like rounding to the closest number. You always have to estimate a realistic and reasonable number. So in this case, if we look at those 2 points, you could probably say something along the lines of x looks like it's maybe, I don't know, say 5.3. And then on the other end of things, it could be maybe 0.7. So this is why we want to be as precise as possible in our graph. If your graph is really sloppy, it's going to be hard to get accurate-ish numbers. The other thing to consider is symmetry. So I know that this thing's got to be symmetric. And so for me, I said that this point on the right here is about 0.3 past the point I knew previously. So I said like this little distance here was 0.3. But then for symmetry, the point on the other side also needs to be 0.3. So you can't be throwing out estimations like 5.1 and then 0.7 again, right? So that one is a distance of 0.1 and that one is a distance of 0.3, and you know that's not going to happen. So if the 2 intercepts look wildly different, you might want to go back and redraw your graph and make it look a little bit nicer. All right, wrapping this up with a couple of quick word problems. So I'm going to say a cyclist jumps off a ramp and follows a path given by some function. H of d equals negative 0.1 d squared plus 0.7d plus 2. So you notice this isn't equal to 0 right now. It's just a function. And h and d are height and distance in meters. And so what I might ask you, right, because that's all just set up, the actual question might be something like, how far did she travel before she landed? This is a really common sort of thing to see in a word problem. You got to interpret the words a little bit here. So at the end of the question, we're told she landed. So when something lands, when something is on the ground, you got to ask yourself, how high is it? So when something's on the ground, its height is 0. So to solve this, we're going to put 0 in for our height. So we'll have 0 equals negative 0.1 d squared plus 0.7 d plus 2, and then graph that. Not going to make you graph this by hand, though, so what we're going to do instead is we're going to use Desmos. So I'm just going to flip over to that, where I've got it preloaded and ready to go. Keep in mind, you can't use D. Desmos really only likes it when you use X or Y for your graphing, unless you're doing sliders and stuff. So once you've graphed it, you've got this line here. Nice thing about Desmos is if you click or tap on the curve, you'll notice it picks out a couple of points. Specifically, it'll pick out your intercepts. So we can see we've got intercepts at 9.179 and negative 2.179. So that was pretty easy. So if we switch back, we have 2 options here. So we've got D equals negative 2.179 meters, or we've got d equals 9.179 meters. But if you stop and think about that, one of those numbers doesn't really make sense in the context of our question. She's probably not traveling backwards 2 meters off of the ramp, so chances are it's really just going to be that bottom one of 9.17. And if you stop and think about it by looking at the graph, you can probably imagine that this point here, this 0, 2, that was probably where she left the ramp, and then she traveled through the air from there. So the stuff on the left doesn't actually exist. She just didn't start on the ground, because that's not how ramps actually work. Second word problem. We've got a diver's height above water. So this is, some sort of high-level athlete doing some fancy dives. Is going to be given by h of t equals 0.5 times t minus 4 squared minus 4.5. And so what we want to know is, for this particular athlete, how long was he underwater, right? So h is height, t is time, and how long was he underwater for? So same idea, right? The surface of the water would be at h being 0. So we've got 0 equals 0.5 times t minus 4 squared minus 4.5, right? So height being 0, put 0 in for height. So go ahead, graph this on Desmos yourself. This is one you could graph by hand, but save some time. Graph it on Desmos. Try to interpret the answer and see what you come up with. I've already got it on Desmos myself. So if I hide the last example and then we look at this one, we see we get this graph. So if we look specifically at our intercepts, we've got intercepts at 1 and 7. So 1 second and 7 seconds. When you're doing any sort of application, it's up to you to interpret what exactly is being asked for. In this case, we don't want to just pick one or the other, or both of these even. Underwater is between when you go through the water and when you come back out of the water. So in this case, if you go down at 1 and you come back up at 7, you were underwater for 6 seconds. And there we go. And so that kind of covers our solving by graphing. If you're good with this, keep on moving to 4.2 where you'll learn how to solve by factoring. If you're still struggling with the graphing or the completing the square, make sure you go back to chapter 3 to check out those.